Hello and welcome everyone to the interactive tutorial session. So this is session 11 and so this session is based on content of week 11. I hope I am audible. Someone can just confirm. Okay, thank you. So So to start with the content covered in week 11, so it's on microwave integrated circuits, or in short MIC. So the topics covered under this were planar transmission lines for microwave integrated circuits. So as I hope you have already watched the video lectures wherein you have seen the different types of planar transmission lines, such as strip line, then microstrip line, then slot line, then coplanar waveguides. So these are some of the planar transmission lines which you have seen. So among these different planar transmission lines, so by now you might have already got the idea why what is the significance or need for a planar transmission line. So when you go for an integrated circuits, being planar is very important, and for for the integrated circuits. So to start with some of the features of the different types of transmission lines, say I will just brief some of the things. Say in strip line, so you have seen how the strip line is. So it has a dominant mode of propagation as TEM, that is transverse electromagnetic wave. So that is the wave propagation is perpendicular to electric and magnetic fields. And so hope you remember the field lines, how it was in case of a strip line, in case of a microstrip line. So hopefully you know how all these are. So in microstrip line, we say it is a quasi TEM because the transmission because the structure of the transmission line is where you have one ground plane and dielectric and then conductor. So from conductor to ground plane you have electric field lines, and if you remember, it is a kind of quasi TEM mode of wave propagation. And similarly, you have come across slot lane, which has a TE wave propagation. So all these are just giving a brief of what had been covered. So coplanar waveguide, if you remember, that's one of the very important structures wherein you have on the same plane, you have the two the center conductor, and these are like ground plane. So on the same plane itself you have the ground plane as well as the conductor. So this is the speciality of a coplanar waveguide. So so these are this is very useful in case of easy mounting of lumped elements in shunt or series configuration. So these are some of the things which had been covered. So I haven't gone through all, but still. Okay, then the topic of discussion was lumped elements for microwave integrated circuits. So when I say lumped elements, you have to remember uh, resistor, inductor, and a capacitor. So these are all the lumped elements. So these elements for microwave integrated circuits, how to realize these kind of elements in case of microwave integrated circuits, this was discussed. Then to brief on monolithic microwave integrated circuits and also hybrid microwave integrated circuits. So I am not going into the details of each of these. So let me go to some of the questions so that we can discuss in between some of the theory and some numericals as well. So to start with the first question, so this question is on, I think the question is on a microstrip line. Okay, so just to give a brief idea of how the microstrip line looks, so this is just to brush up the concept. You have to go through the video lectures in detail. So this is your conductor, and this here you have a ground plane. Here you have a ground plane, and here you have the conductor, which is having a width W and having a thickness or height H. And so this is a dielectric substrate. So this is the microstrip line. So the question is, keeping the dielectric constant and thickness of the dielectric layer same. So let me just tell you what is this. So let me denote this as T and this as H. Okay. So H is the height of the dielectric substrate and epsilon R is the dielectric constant of the substrate used. If the width of the strip, so width of the strip means W. So W, or the width of the strip or the microstrip, is being changed. So it is being decreased. So if the width is decreased, what will happen to characteristic impedance of the line? To answer this question, you must be knowing what are the parameters on which the characteristic impedance of a microstrip line depend on. So you have come across the equations. If you have any, if you need more clarification, you have to go through the equations in detail. So based on the characteristic impedance equation, so let me write one equation, that is in case for W by H greater than or equal to 1, okay, in such conditions, that means width is much greater than height. Okay, so in that kind of a case, okay, Z0 or the characteristic impedance can be written as 120 pi divided by root epsilon effective into W by H plus 1.393 plus 0.667 ln of W by H plus 1.44. So from this equation, it is very evident what are the parameters on which the characteristic impedance depends on. And you know that epsilon effective is not equal to epsilon R. So it is an effective dielectric constant. If you go into the details, you will get the equation for that as well. So from this, it's clear that as the width of the strip is decreased, keeping epsilon R and H as constants, if width is decreased, Z0 is definitely going to increase. So the statement here is true. I hope this is clear. You can look at the other case also. You can look at the equation from the video lectures. What is the equation for W by H less than 1 as well. So and based on that you can come to this conclusion. As the width decreases, keeping the dielectric constant and height as constant, then the characteristic impedance is going to increase. So I hope I can go to the next question. Okay, let me read this question. This is again a true or false question. Let us read the statement. For a microstrip line, again the question is on a microstrip line, the effective dielectric constant, that is epsilon effective, so which is not equal to epsilon r. Please note that point. So this effective dielectric constant is given by C divided by Ca, where Ca is the capacitance, per unit length. Okay, so I can write it like capacitance per unit length, with air as the dielectric. Say if you imagine there is a parallel plate capacitor where you have a dielectric in between. In that case, there is capacitance can be written like epsilon 0 epsilon r A by D, where D is the distance between the plates and A is the area of the plate. Okay, so this is the case when epsilon r or dielectric is present. If air is the medium between the two conductors, in that case I can write it like epsilon 0 A by D. Now, so this is being denoted like Ca. Okay, so if you observe this, you can understand or you can intuitively say whether the statement is true or false. So this is a Ca denotes the capacitance per unit length when air is the dielectric. Okay, and C denotes the capacitance per unit length when or with dielectric, having a dielectric constant of epsilon r. So if you intuitively look at this, C by Ca, the ratio C by Ca is epsilon r. So that means it's a ratio, or here it's not equal to epsilon r, because in case of a microstrip line, epsilon effective is different from epsilon r. So in a microstrip line, to be specific, epsilon effective is epsilon r plus 1 by 2 plus epsilon r minus 1 by 2 into 1 divided by root of 1 plus 12h by w. So this is the epsilon effective. So that comes because this is this microstrip line with the ground plane here, and this is the strip. So this is in air. So this strip is going to see air above, and below that you have a dielectric. So that is the reason here you have an average of epsilon r plus 1 by 2 and then epsilon r minus 1 by 2 into it also depends on the width of the strip and also depends on the height of the dielectric substrate. Okay, so epsilon effective is not equal to epsilon r. Now the question here is whether this is true or not, false. So yes, this is a ratio C by Ca. Okay, so this is a true statement. To add to this, you all know that refractive index is square root of epsilon r. Okay, so if you look at refractive index, in terms of refractive index, say if you have a wavelength, okay, so how do I say lambda g, that means the wavelength in the dielectric or wavelength in the medium. So I can write it like lambda naught by n. Okay, so and I can say, or I can say n is equal to lambda naught by lambda g. You already know that n is root epsilon r. So root epsilon r is equal to lambda naught by lambda g, or I can say epsilon is equal to lambda naught by lambda g the whole square. Now let me just make a small modification here. In case of a microstrip line, this is nothing but epsilon effective, so that is also equal to lambda naught by lambda g the whole square. So if you come across the video lectures, you will see both of these equations. Epsilon effective is the ratio of C to CA, and it's the square of lambda naught to lambda g whole square. Okay, so just adding this point here. Hope this is clear. These are all very simple statements. So okay, let's go to the next question. This is on a coupled strip line. Okay, so just to tell you how, maybe you already know that, but still I would like to give so what is this coupled strip line? So here if you have, so this is one strip and this is the second strip, and here you have the ground plane. Okay, so this is our coupled strip line. Okay, and this is the width of the strip line. It's a coupled strip line, and this is the height of the dielectric. So this is dielectric substrate. Okay, so the question is about this strip line, coupled strip line. Let C11 and C22 represent the capacitance between strip conductor and the ground plane. Okay, C11 and C22. So that means between the first conductor and the ground plane, between the second conductor and the ground plane. So it is C11 and C22. Okay, let C12 represent the capacitance between the two strip conductors. Okay, so C12 is the capacitance between the two strip conductors, and if the strip conductors are identical in size, okay, so this is a very important statement. What happens when the strip conductors are having identical size? That means width is same, thickness is same. In that case, C11 will be equal to C22 will be equal to C. Okay, so that means the capacitance between the strip conductor and the ground plane will be same if the strip conductors are identical in size. Okay, now in case of odd mode excitation, C0 is equal to C11 plus 2 times C12, where C0 is the capacitance of either of the line to the ground. Okay, so let me just brief. So here, as I said, C12, that means it's a capacitance between the two strip conductors. So it can be written as C0 minus C11 or C22. Both are same. So I can write it as C by 2. So C0 is equal to 2 times C12 plus C. So where C is, it can be C11 or C22. So 2C12 plus C11. I can write it like that, or I can write it like C1 to C22. So, this is a true statement. So hope you have gone through the lectures wherein coupled strip line is explained, and this has been explained in detail where how to calculate the capacitance between the two strip conductors. So it is C0 minus C by 2. Okay. So let's move on to a numerical. So to do this, before going into this numerical, let me try to just give a brief of what is the concept of inductor and parasitic capacitance. Say any inductor, so this is a very fundamental concept which had been already discussed in the video lecture. So let me just brief that. Any inductor, say L, this is associated with the parasitic capacitance. Okay, this is associated with the parasitic capacitance which comes in parallel with this inductor. Okay, so that is denoted like Cp. Okay, so effective inductance is different from this inductor value L. So this effective inductance can be written like this. The value of inductance L divided by 1 minus omega by omega p the whole square. Okay. Now let me tell you what is omega p and what is omega. So omega is the frequency at which we are looking at, or the operating frequency, I can say that. So omega p, so here the omega p is 1 by root L Cp. Okay, omega p is 1 by root L Cp. Okay. Now here, so this concept is needed to solve this numerical. So let me go to the question now. If the inductance of a 5 nanohenry inductor is 10% higher than the nominal value at a frequency of 2 by pi gigahertz, neglecting the series resistance value of parasitic capacitance. So here there is an assumption, very important assumption being made. Here when I say inductor is associated with the parasitic capacitance, inductor has leads which has resistance. So that is a series resistance. So here the assumption made is we are neglecting the series resistance. So neglecting that, we have only this capacitance which is coming in parallel with the inductors. So in that case, so the LE, so LE is different from L. So effective inductance is different. So how do we calculate that? We will come to that. Okay. So the question is, from the question, let me write down the inductor value is L is equal to 5 nanohenry and effective inductance, that is 10% higher. So what do you mean by 10% higher? 5 plus 5 into 10 by 100. Okay. So 5.5 nanohenry. Okay. And the operating frequency is given. F is equal to 2 by pi gigahertz. Okay. So what is omega? 2 pi f. So 2 pi into 2 by pi. Giga is 10 power 9. Okay. So pi cancels. So omega is 4 into 10 power 9. Okay. Now let me come to this equation. So from that equation what I can tell you is LE. So that is LE. So LE is known to us. It is 5.5 into 10 power minus 9. That's equal to L. That is 5 into 10 power minus 9 divided by 1 minus omega. Omega is known to you. 4 into 10 power 9 divided by omega p, the whole square. Okay. So from this omega p can be calculated. So once you simplify this, omega p will be 13.33 into 10 power 9. So we know that omega p is 1 by root LCP. Okay. So 1 by root of L is 5 into 10 power minus 9 into Cp is equal to 13.33 into 10 power 9. So Cp can be calculated from this. So you will be able to do the simplification and get the answer as 1.125 picofarad. 1.125 picofarad. You can try this. You can try this out and find. See whether you are getting a matching. Hope this is clear. Any doubts, please ask. Okay, I hope there are no doubts. So let me tell you. So now in this question I have told about an inductor associated with a parallel capacitance or the parasitic capacitance. So let us look at another question. Okay, let us look at this question wherein you have along with the capacitance or along with the capacitor, you have an associated inductor. Okay, so you have an associated inductance which is Ls and that is coming in series. So the effective capacitance is not same as this capacitor value. So that can be written as effective capacitance CE is equal to capacitance C divided by 1 minus omega by omega S the whole square. Okay, where omega S is 1 by root of Ls into C. I hope this is clear. This is a very similar approach. That's why I am just trying to solve this question as well. So let us read the question. Nominal value of a capacitor is 20 picofarad. So nominal value of the capacitor is given. So that means C is given to you 20 picofarad. Parasitic inductance. That means this Ls is given to you. Ls is 0.2 nanohenry. Value of the capacitor at a frequency of 1 by pi gigahertz. So now you have to calculate the effective capacitance at 1 by pi gigahertz. So let me tell you, F is 1 by pi into 10 power 9, and you need to calculate CE. Okay, so to calculate that, what do we need is omega S. Omega S is 1 by root of Ls, 0.2 into 10 power minus 9 into C. Capacitance is 20 into 10 power minus 12. Okay, so if you calculate this, you will get omega S. So I am just giving the final answers. You can see whether you get this. 15.8 into 10 power 9. So this is omega S. Please note that. Say if you want to write Fs, it is omega S by 2 pi. So that will be 2.514 into 10 power 9. Okay, because here we have a F, and let this be Fs. It will be easy for us to solve. So CE will be C, 20 picofarad, 20 into 10 power minus 12 divided by 1 minus omega, or instead of omega by omega S, we can write F by Fs, the whole square. So that will be 20 into 10 power minus 12 divided by 1 minus F by Fs. So this is F 1 by pi divided by 2.514. 10 power 9 gets cancelled. So 2.514, this thing whole square. Okay. Once you solve this, you will get the value of effective capacitance at this particular frequency, 1 by pi gigahertz. So that is not 20 picofarad, it is 20.3 picofarad. So once you solve this, you must be able to get this. So the answer option is C. Hope this is clear. Any doubts you can ask. Okay, if there are no doubts, I will go to the next question. So we stopped at actually question number 4, and let me go to question number 5.
Ma'am, can you kindly show the previous slide? I forgot to take the screenshot. Thank you, ma'am. Thank you, ma'am.
Yeah, okay. So let's move to the question on this resistor. Okay, so this is a question on realizing a resistor using this strip line. So to start with, so all of you know the fundamental relation, that is resistance is rho L by A. So resistance is resistivity into length divided by area. So when we realize this resistance using a strip line, then this area, so area is nothing but the width of the strip line multiplied by thickness of the strip line. So this is the area, and length is nothing but length of the strip line. Okay, so this L is the length of the strip line, this A is the area, which is W into thickness, and rho is resistivity, that is a material parameter. So 1 ohm, okay, let me go to the question. 1 ohm planar resistor is to be made using a resistive material having a resistivity of 10 power minus 6. So we know the value of resistance to be made, that is 1 ohm, and we know the resistivity also, that is 10 power minus 6. And the width of the strip used to make the resistor, so that means the width of the strip line is 5 times that of the thickness. Okay, so the strip line, you know what is the width and the thickness, so width is 5 times the thickness. And also it is being said that the length of the strip line, that is 20 micrometers. In that case, the question is calculate the thickness of the strip, thickness of the strip conductor. Okay, so how do we do this? We know R is equal to rho L by A. So the resistance to be realized is 1 ohm with a resistivity of 10 power minus 6, with the material having a resistivity of 10 power minus 6, and L is 20 micrometer, that is the length of the strip, and A is area, which is width into thickness. Okay, so and width can be 20 into 10 power minus 12 divided by width can be written as 5 times thickness into T again. So T square will be 4, 20 by 5 will be 4 into 10 power minus 12. Therefore T is 2 into 10 power minus 6, or I can write it as 2 micrometer. So this is the thickness of the strip required. So that is 2 micrometer. The answer option is D. So this was a question on realizing a resistor using a strip line. Hope this is clear. So this is one lumped element, realization of a lumped element using this integrated strip line technique. Okay, let me move to the next question if you don't have any doubts. Okay, so this is a very simple question. Hopefully, I think you can answer this. What is the dominant mode of propagation in a strip line? Whether it is TEM, whether it is TE. Yes, it is true. Okay. So the dominant mode of propagation in a strip line is TEM. Can you please comment on what is the dominant mode of propagation in a microstrip line? Dominant, all of you can really use the chat. I can see the chat window. You can comment on what is the dominant mode of propagation in case of a microstrip line. Okay, so let me tell you what is this dominant mode. Yes, as you said, dominant mode is nothing but the one having the lowest cutoff. That is fine. My question is whether it is TEM or TE or what. So as I mentioned before, microstrip line is having a quasi TEM. I had mentioned the reason also. Say if you remember the structure of a microstrip transmission line, you have a ground plane and then you have this conductor here. Conductor is having a width. Okay, so the conductor width is smaller than the ground plane dimensions. So if you remember clearly, it was mentioned the electric field lines, if you remember. So it used to be like this. So it's a quasi TEM. So electric field lines is from one conductor to the other conductor, and obviously this is from the conductor to the ground plane. So if you look at that, the dimension, because the strip width is smaller, we don't have the really the straight lines. We have kind of this kind of lines. So this is a quasi TEM mode of propagation. In case of a strip line, we have the strip and conductor above, I mean the ground plane above and below. So it's a TEM mode of, purely TEM mode of propagation. In case of a microstrip line, it is a quasi TEM mode of propagation. So let's go to the next question. Okay, so this question is on realizing a capacitor in a monolithic integrated circuit. So, so to discuss this question, okay, let us read the question once and then try to understand about realizing capacitor using a monolithic integrated circuit. So capacitor in a monolithic integrated circuit has a capacitance of 0.1 picofarad. So the capacitor we are realizing is 0.1 picofarad. Capacitor plates are separated by 0.1 micrometer. So let me tell you, any capacitor, we say that the plates separation, these are some basic parameters, 0.1 micrometers. And the dielectric constant of silicon, so the dielectric used here is silicon, and that has a dielectric constant value of 11.7. So let me try to write epsilon r is 11.7. If the capacitor plates are square, that means this is a square plate. Okay, so this is a square plate and this is the distance between the two square plates. Okay, now the question is each side of the capacitor plate. So when there is a square, you have AA, and what will be the area? Area will be A square. So I hope by now you got a clue of how this has to be solved. So all of you know that C is epsilon 0 epsilon r A by D. Now we know what is epsilon r because silicon is used. Epsilon r is 11.7. The value of epsilon naught is known to everyone, and the capacitor value to be realized, that is also given, 0.1 picofarad, and D, the distance between the plates, or the plate separation, is also given. Now the only unknown parameter is the area of the plate. So this area can be calculated. Once you calculate the area, we know that area is square of length, or length side of the side of the plate. So that small letter a, or the side, will be root of capital M. So to solve this, let me try to write this. 0.1 picofarad, epsilon 0 is 8.85 into 10 power minus 12 into epsilon r is 11.7 into A, divided by D is the plate separation, 0.1 micrometers. Can anybody please let me know what is the area? Can you all try to calculate and give your answers in the chat? Very simple to calculate. Please try. Once you get the area, you can find out the side of the capacitor plate. If anybody can get me the final answer, that's also fine. You can try, all of you can try. There are no responses. Okay, so let me just give away the answers. I hope you will try. Please do try. So the area is 0.965 into 10 power minus 10 meter square. Okay, so the side of this, yeah, I got some answer, 9.8 micrometer. Right. That's a right answer. Thank you for responding. So the square root of this will be 9.82 micrometers. See, if you just notice, the unit is micrometers, so you have to please note such kind of hidden things in the question, so that you will be able to answer the question properly. So this is the final answer, 9.825 micrometers. So that's all for today's discussion. Thank you everyone. Like, if you have any doubts, you can ask them, or we'll close the session. If you want me to repeat any of the questions, or if you have any doubts. Okay, let me go to question number 2. Okay. May I know, is there any particular doubt, or you want me to repeat that, or? Say, this is basically a true or false question. So we are just looking at the statement. The statement is that in case of a microstrip line, that is this kind of a microstrip line, the epsilon effective. So epsilon effective is okay. So your doubt is epsilon effective is epsilon r plus 1 by 2. Yeah, okay, fine. So that is fine. So this is the formula for calculating the epsilon effective. So this epsilon effective is also equal to the ratio of C to C by CA. C to CA. Okay. So I think I tried to give a convincing, intuitive answer with the help of epsilon r. So please don't confuse here. So I was trying to give an idea of what it looks like in case of a normal capacitor, I mean parallel plate capacitor case. So now this is not a parallel plate capacitor. When it comes to a microstrip line, it's not a parallel plate capacitor. I told you the width of this strip is smaller compared to the dimension or the size of the ground plane. So we can't consider it like a parallel plate capacitor. So it's having its epsilon effective is not same as epsilon r. Okay, but if you remember, basically what is epsilon effective? That is the ratio of C to CA. Okay, so please take that in that sense. I hope this seems convincing. Okay. Any other doubts? Thank you for pointing out, Prashant. Okay, question number 1. Okay, question number 1 is something very evident from the equation. So So the question is, say if you keep the epsilon r and height, I mean the dielectric constant and height constant, and if you reduce the width of the strip, what will happen to the characteristic impedance of the transmission line? So H is kept constant, epsilon r is kept constant. If you reduce W, what will happen to Z naught? So Z naught is definitely going to increase. Any other clarifications? So if there are no doubts, I'll close this session. Okay, some question. Is it possible to post your today's problem solving session in microwave engineering website? Yeah, I'll be posting in the YouTube channel, and the link will be uh, uploaded in the same um, Excel sheet which you will see um, once you click on to the NPTEL page. You will see the Excel sheet wherein week wise problem solving session and the link is given. So that link will take you to the YouTube say, channel and particular video. Okay, thank you. Regarding assignment solutions, okay, so this is being dealt by another set of team members. I will definitely let them know your request. uh, so hopefully it will get uploaded very soon. Okay, I think okay, there is something else for exam. Previous year sample questions. uh, okay, so this is not really available as such, but maybe you can write in the discussion forum. uh, so basically this assignment questions are really if you are able to solve these assignment questions on your own, really understanding the concepts, you will definitely be able to do the final exam as well. I don't know whether it is available, but I can still check with that. But please do write in the discussion forum so that you will get a quicker reply, or maybe you can get any links or something like that. So, it would be MCQ or true or false if you ask me. That purely depend on the professor's wish. So there will be MCQs, there will be true or false questions, there will be numericals. So I can't say really. So it will be something very similar to the assignment questions. I think I'll close the session if there are no other clarifications needed. So thank you all for joining. So meet you all next week for the last session. That will be for week 12. So hope these sessions are helping you out to solve the weekly assignments. So thank you for joining. Yeah, bye.